Okay folks, Tom Barbalet here in the San Francisco Bay Area. I just wanted to run some numbers and also talk a little bit about the development that I'm working on currently with Noble Ape, my simulation. NobleApe.com, github.com/Barbalet, which is my surname /Noble Ape, all one word. So, for years now, the Noble Ape Simulation has been based in land tiles, which are these things. Now this is actually roughly half what you'll see, or half, well, a quarter. You'll see 4 of these if you run the simulation normally. But the simulation is based in these land tiles, and each of these land tiles is 256 by 256. I've got a little text file here. Oh, sorry. So the land file is 256 by 256. And these are then multiplied by 8 to get down to the resolution that you see here. So we go back this. So this is a rounded down, and then there's no more interpolation here. This is just the kind of rendered resolution. These little red dots represent the Noble Apes. So each of these dot points that the ape coexists in is roughly maybe, I don't know, maybe 6 feet, maybe 2 meters, let's say. So in these tiles you have basically about 4 kilometers. So each of these tiles represents 4 kilometers, so that's a kilometer, that's a kilometer, that's a kilometer, that's a kilometer. So maybe 4 kilometers is about 2 and a bit miles of that kind of order. So these are the base units that Noble Ape Simulation runs with. What I'm looking to do is actually distribute the Noble Ape Simulation over a number of machines. In fact, I'm probably going to start this with the iPhone version of Noble Ape. So what I want to do is actually get a sense of how big I need to make the simulation environment in order to do that. And that's what I'm running these numbers for. So one of these squares equals that in meters. Let's just say that in kilometers to make it easier. And then let's look at the planet. So Earth is this many kilometers, basically. So if you ran the math on this, it's what? 8 8s are 64, so it'd be what? 1600 of the Noble Ape units worth of tiles. So Noble Ape isn't a sphere, it's a toroid, which has interesting mathematical properties but maintains its coherence. It's almost like the Noble Ape toroid. If you imagine one donut, and then you imagine another donut that kind of comes from the hole and goes round it. That's always been the model, where the light source is the other donut, and the other donut kind of rotates around the main donut. And yeah, there are very interesting properties associated with how sunlight is maintained through that, but that's always been the hypothesis. So I will need roughly 1600 by 1600 of these Noble Ape land units. And there are, as we go through here, there are a number of different possibilities that you can do here. This is so much faster on the other machine. Anyway, so in addition to this, obviously you'll need sea areas as well. There is also a weather simulation, which is not very easy to see in this circumstance. Let's just create a new. A lot of land here with a lot of weather on it. But yeah, you have this weather simulation that exists too with the landscape. and this will need to be simulated as well. So these kind of numbers indicate that you'd need roughly 1 million iPhones, say. Actually, probably closer to 4 million iPhones to get a reasonable simulation space. The breakdown will probably be 30% land, 70% water. Actually, it's probably going to be closer to 50-50 because the percentages of land and water on these, if you go back here, there's actually probably slightly more land, slightly more water than land in most of these. So if you move to a 50-50 ratio of these land-water tiles, you'll end up with something that's very close to Earth-like standards. And just based on the problems of... so what that means is that for all the tiles, half of them will be just water. And then the other half will be the water-land tile combinations that folks have kind of grown to expect with Noble Ape. So you'll have a series of these kind of interlocking land-water groups, and then you'll just have water for the remainder. And this will be fractally spread, very similar to the fractal generation that's used to create the land-water currently, the topologies. So my initial aim is to not have something... This is actually considerably larger than the Earth. If you think of a toroid, the surface area of this arrangement would be larger than the Earth. I can't do the toroid mathematics off the top of my head, but it's got to be at least 3.5 times. I think there might be like an extra pi factor somewhere in there. So yeah, it's a substantial size larger if you do it as a toroid. So my aim initially would be to do probably something closer to 512 by 512, which is in the order of kind of half the size of the Earth associated with the simulated area. And what this would be is 512 by 512 unique seeds, and the seeds are actually defined as two 16-bit numbers. So basically I would need to have uniqueness over an area, and let me just do the math here, but whatever 512 by 512 is. So certainly well less than the two 16-bit unique numbers, but I still need to test uniqueness when I create this. And what will happen is that rather than having 2 by 2 as it is currently for the current simulation, there will be actually 4 by 4, with the view that the active Noble Ape will be in one of the central 2 by 2. So you'll end up with something... why did it just do that? That's very interesting. So you'll end up with... So this is the standard one currently, where you have 2 by 2 blocks. And each of these is 256 by 256. But what I will do is create create 4 by 4 with the view that the ape will be in these active ones, and these surrounding ones will be additional simulation for weather and what have you, and other incidental apes. And if the ape moves, so, I mean, assuming this is like, so, if this is 0, 0, for example, and this is like 0, 1, dot, 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 and this is 1, 0, 1, this is 2, 1. This is 2, 2. This is 1, 2. So what will happen is these are the coordinate squares that the ape is moving around. These are the coordinate tiles. And then when the ape moves down here, it will add the additional tiles here and here. And these will probably be cached. I'm still working out the caching strategy, but there will probably be a caching of the surrounding tiles. Maybe 20 or so surrounding tiles will be cached just to avoid the generation time associated with this. So you get a sense on this computer, and this is a whole bunch of other gumph as well. So I mean, don't judge this completely because it's got brain generation and a wide variety of other stuff that doesn't need to. And actually, it actually creates new apes. But this is the kind of generation time. Unfortunately, it's probably only about a quarter of this time. It's just on a slow machine as well. So yeah, each of these generation times will occur when an ape moves out of here, and really what will happen is, as the ape traverses into here, still got a lot of stuff going on around it, and these other sections will regenerate. So there's a kind of real-time generation component here, where I don't want the simulation to kind of seize up as these new sections are being generated. I just want them to be kind of created. And obviously in the case where if 50% of them are just straight water, most of these moves, well, half of them, would just be associated with the addition of water squares, with maybe 1 or 2 land squares. Now, obviously, I mean, if they traverse diagonally, this is going to, generate more squares. But, all this will be worked out. And the idea is almost that we'll have a kind of land server, where eventually a majority of this will be cached. And very similar to, the way Google Maps operates, for example. It could be possible for this caching to move, just to be things that are server downloaded, basically. You'll have a land server that will just maintain land and weather information and just kind of keep updating that. So, all this is possible. The way I've thought about it currently is just with regards to individual machines kind of distributing this mathematics. So what I'm doing currently is actually rewriting the way the landscapes and weather is calculated, with a view to move to this model ideally in the next few weeks, and just start it out with the view that you'll have a simulation where, when the apes move, they'll move across these kind of boundaries and the landscape will recalculate. And through this also there's an idea of what I'm calling non-player character noble apes that don't have the full cognitive component to them, but are still like simulated entities that the apes can interact with. And I'm interested in creating kind of noble ape light noble apes that can move through this simulation space without the processing difficulty, with the view that they're just like actors in the various environments. And my feeling is that there's probably going to be like an 8-to-1 ratio, maybe a 7-to-1 ratio of these kind of player character noble apes being the rich ones with a full cognitive simulation, and then just a bunch of actor noble apes that exist in the environment and, play, very similar to the Truman Show kind of thing. Play characters in the simulation. With the view that this is just, we've got to work out the initial kind of processing, network balancing, juggling associated with this. So I'm just trying out these ideas. Anyway, I'm going to throw that out there, create a YouTube video and give people a sense of what I'm working on currently, with the view that all of this is taking time. But there's a lot of source code changes currently. You can follow that through GitHub /Barbalet, which is my surname, /Noble Ape. You'll see the changes going progressively. And I don't want to break anything currently too. The Windows version I think has been pretty well broken for a while, but I'm maintaining a Mac and an iOS version continuously, with the view that everything that's developed for the Mac will translate to the iOS version. I prototyped an iPhone version. The main thing is using the topological terrain view, so my preference for the iPhone was to do this kind of stuff, because obviously it scales and you can do this kind of movement. But I think what I'll probably end up doing is just doing a top-down, particularly if I get the map movement, so as the Noble Apes move from map area to map area. they'll get the refresh accordingly. And I think that's probably very good feedback. It may be computationally intensive for the phones. I've got to just see how that pans out. But it'll probably be a 5S kind of cut-off just because of the processing required for this stuff. And obviously on the Mac, I mean, this is an older Mac, but on the newer Macs, the 8-core processor, what have you, it's just absolutely phenomenal. I need to record a video on one of those just to show how fast you can get. You can get up to, I'm seeing speeds of, 30,000 plus 8 brain cycles per second, and when you remove the cognitive simulation component, you end up with something that's distinctly, let's get some good cognitive simulation noise in there. You end up with something that's distinctly faster, and you can get into the hundreds quite comfortably, hundreds of thousands of 8 brain cycles per second. It really is extraordinary. In fact, I added a feature to turn off the daylight and the tides, because the strobing of the light changes in the tides was just so great. Anyway, Tom Barbalet in the San Francisco Bay Area, just recording an update associated with the Noble Ape Simulation to get an indication of what I'm working on currently in terms of like a vast simulation. Anyway, Tom Barbalet signing out.